Okay, so I want to start reviewing. Okay. Um, now, I'm gonna today and Monday I would review. Because this is a chapter is a lot more involved than unit one, and so I'm gonna do a lot of review. Okay, I'm gonna hit on carbs. There's a couple aspects of carbs that are particularly challenging. One is the Benedict's reaction. And the other one is the um, ketal and acetal reactions. So those are the ones I'm going to focus on because those are what most people have the most trouble with. Okay, so these are the carbs you need to know. This is a worksheet under Canvas files, um, Unit 2 worksheets. And it's called carbs worksheet. Okay, so this is a lot like the format of the test. I'm going to ask you, I'm going to talk, and I'll show a structure. I'll ask you some questions about it. These are the 4 questions. Name the molecule, alpha beta status as well. Name the linkages, if applicable. Show the Benedict's reaction for each. Is this carb a reducing sugar? Why or why not? So each one of these structures, I'm going to go through those questions. Okay, so let's start with this one here. Okay, this is galactose. We know it's galactose because of carbon number 4's hydroxyl group goes up. If it went down, it'd be glucose. Okay, so name it. This is, and it's an alpha because the carbon number 1, the is going down. And the anomeric carbon. We put a dot on the anomeric carbon. So that's going to be alpha galactose. Okay, name the linkages. There are no linkages. Linkages are only on di, oligo, and polysaccharides. Monosaccharides, there are no linkages. Okay, name the Benedict's react or show the Benedict's reaction. Okay, the Benedict's reaction is going to be step number one is show the opening of the hemiacetal to an aldehyde. Okay, so here we have the OCO. It's got an OH group and it's got a hydrogen group. So this is a hemiacetal. It will give a positive test. And if it's a positive test, it is a reducing sugar. Okay, so let's look at the reaction. Step number one is showing the ring opening up. Okay, it opens up and exposes an aldehyde. Now, that aldehyde is susceptible to oxidation, and that's what will give a positive Benedict's test. Benedict's test starts with carbon 2. Should be not carbon, copper 2. So the aldehyde goes, and this is in a basic environment. So we're going to get the acid salt when the aldehyde goes to the acid. Okay, so copper 2 goes to copper 1 through reduction. The aldehyde goes to the acid salt through oxidation. And they have to happen together, no exceptions. So this is the acid salt. And this copper plus 1 is the orange solid that you see. So this is blue. Okay, so we're going to go through that on each one of these structures. Okay, any questions about this guy? Yeah.
Go back to
Okay, a hemiacetal can convert back to its original aldehyde. And that's the process that's going through here. So here's the aldehyde. That's the hemiacetal there. So it goes aldehyde, hemiacetal, acetal. And those are two-way. And they happen to be in the same molecule. frequently they're separate molecules, but with carbohydrates, they're cyclic and they're in the same molecule. Okay, so that's galactose. Now this is going to be exactly the same if we started with glucose. The only difference is this guy here, this carbon number 4 hydroxyl group is going down. This reaction down here is exactly the same. It's got a hemiacetal present for the same reason. So this works for glucose also. The only difference is going to be this is going down. That's the only difference. Okay, let's. So the glucose is in the blue.
You always add that warming water with the H that was on that, the anomeric carbon thing.
Okay.
The OH that we're adding.
Yeah, that's just basic water.
Okay.
That's like sodium hydroxide mixed through the water.
And then that carbon's pulling the oxygen that we get right here, right?
The
The carbon, the anomeric carbon, when we take away that hydrogen, it's pulling the oxygen, right?
Yes, there's a hydrogen on that anomeric carbon. Yes, right here.
Why does it pull an oxygen instead of another hydrogen?
Oxidation reduces the number of hydrogens. So that's why aldehydes can oxidize. Ketones don't have a hydrogen there, so it can't be oxidized. So you're not dealing with oxygens, you're actually adding them. When you're going, you need to have the last step of going to a full-blown acetyl, you're actually adding oxygen. The oxygen is coming from the alcohol. Okay, so this is beta glucose. And because it's a monosaccharide, there's no linkages, only with di and oligo and poly. But if everything's the same, except the name is different, all these are the same with glucose, only with the blue change. Okay, so this is fructose. So fructose, let's look at fructose now. All right, this is the anomeric carbon for fructose, and that's carbon number 2. Carbon number 1 is if it's a 6-sided heterocyclic ring, it's a 5-membered heterocyclic ring, it's carbon number 2. That's the anomeric carbon. Okay, so the OH attached to the anomeric carbon is going up. So it means this is beta fructose. And there's no linkage because it's a monosaccharide. Benedict's reaction. Now, fructose is one of the exceptions because it's a ketose. So when it opens up, it's going to turn into a ketone. So step number one is this right here, the OCO is going to open up. We have OCO. And hydroxyl is present. And no hydrogen. That means it's a hemiketal. Normally, hemiketals cannot be oxidized except when there is an OH group next to the anomeric carbon. Then they can be converted to an aldehyde, hence it can be oxidized. Okay, so what you're going to have is okay, so here's the ketone right here. This is a switch up for fructose, how it converts to an aldehyde, right? At that step there. Okay, so we've got reduction. And this is going to be the orange solid. And then we have oxidation. So fructose is a little tricky. It does an extra little cutesy step there to convert the ketone into an aldehyde. This is one of those exceptions. Do you have a question?
Yeah, the double bond.
Yeah.
Double bond.
Yeah, because we're in a basic environment. That means it's going to pull off that hydrogen. Because it normally would go to the acid, but because we're in a basic environment, that H is pulled off the acid. So this is the acid salt. So yes, it's a reducing sugar. Okay, so what do we have here? First of all, it's beta. Because it's an MESTL going up, beta. And what are the two molecules there? Okay, this is glucose, and that's glucose. The linkage is an alpha 1,4. Two glucoses with an alpha 4 linkage means it's maltose. Okay, so what does this look like then? Okay, we've got two anomeric carbons. We've got one here, and we've got one here. Each one of those is going to be, we have to analyze. So this one on the left, we're going to go OCO, and it's got a no OH here, and it's got an H. So that means that is a acetal. And the other one is over here. It does have an OH and it has an H as well. So this is a hemiacetal. And this is the one that can be alpha or beta. And because the OH goes up, it's beta. All right. Now, because it's got a hemiacetal, the Benedict solution is going to be positive because that's the part that's going to be oxidized. The other part on the left is not going to be touched because it's a full-blown acetal. So we're going to start with the original molecule. Now on the right is going to open up. So we're going to add copper +2. In a basic environment. So now this part over here is what's going to become oxidized. This part cannot be touched because it's not a hemiacetal. Okay, so maltose will give a positive Benedict's test, hence it's a reducing sugar. So the basic reaction is the same, it's just got a lot of extra structure tagging along with it. Okay, we okay with that? Okay, this is a disaccharide, so let's identify it, each part. So this is going to be galactose. Because that carbon number 4 OH is going up rather than down. And this is glucose over here. And this is a beta 1,4 linkage. Because the original galactose hydroxyl group is going up. So this ends up being beta lactose. All right. Name the linkage, beta 1,4. All right. So let's run this through a Benedict's test. So we have to analyze what we've got here. Okay, over here on the left, that's galactose, and we have an OCO. We have a hydrogen and no OH. So that means this is a acetal. So we have anomeric carbons. We have OCO, OCO. And hydrogen, yes, and OH, yes. So this is a hemi acetal. So the hemi acetal can open up. When it opens up, it can be oxidized. All right, so let's open it. What we're gonna open up is we're gonna open up this part right here. Not the one on the left. One on the left is a full-blown acetal with no OH on that. Oops, I made a mistake. So now I have the aldehyde right here. And throw in some copper +2. That's going to oxidize that aldehyde. So this means it's a fact that it can be oxidized means it's a positive reaction for Benedict solution. Goes from a pretty blue to an ugly orange. Now, every one of these has got the same reaction. It's just the structure that's attached to it is different. It's the only difference. And what do we have here? Okay, we've got glucose up here. And we have fructose down here. Now, this is neither alpha or beta because the anomeric carbons are not hemiacetals, they're both full-blown either ketal or acetal. So let's analyze this one up here. OCO H, no OH. No. So that means this is an acetal. The linkage, okay? Because the anomeric carbon OH goes down. So that means this is going to be an alpha 1, 2 beta. As this OH on the bottom one goes up, that's carbon number 2.
There's no H.
Again?
If there's no H, doesn't that mean that the ketone?
Yes.
So you were asking.
The bottom one's going to be a ketel.
Oh,
Oh, I see what you mean. Yeah. You are certainly right. I have my mind on the. So this one is going to be OCO, H, no H, and OH, no H. So this is going to be a ketone. Thank you for catching me on that. Okay, so there's no hemiacetal to open up. So it's not a reducing sugar. So no Benedicts for the. So Benedict test is going to be negative. Hemis are the only ones that can open up. Okay. What do we got here? Okay, we've got fructose down here. Oh, this is sucrose, by the way. So this is an illegal saccharide. And is there a hemiacetal present? No. So this is raffinose. Linkages. Okay, so this linkage here, there are 3 linkages. Yeah, the linkage down here is going to be a beta 2 alpha 1. This linkage here is going to be an alpha 1 beta 2. This linkage here is going to be an alpha 1 6, because this is carbon 6 right here. And is it a reducing sugar? Hemiacetal? Yes or no? No hemiacetal. So let's analyze each one of these. Because this is fructose, I mean, because it's sucrose, not fructose. So no, not reducing sugar. Negative. No. Acetal. Oh, I left off stachanose. Stachanose is going to have a lactose, another galactose added to raffinose. Okay. That's the most complicated one. Okay, so we have galactose, sucrose. Okay, linkages, we've got a alpha 1, 6, alpha 1, 6, alpha 1, beta 2, beta 2, alpha 1. So Benedict's test is negative. So not reducing sugar. Because because there are no hemiacetals. Again, there are three polysaccharides. There's amylose. Linkage on the amylose is an alpha 1,4. Amylose is also called starch. And it's just a long chain of glucoses. Sometimes thousands of glucose long. Okay, these are all acetals. Here's the 1,4 linkage right there. Except for the very end one. And that's going to be a hemiacetal, the very end one. Out of 1,000 that are not, only the one is going to be a hemiacetal. So some people can say this is a weak reducing sugar because of the hemiacetal. A lot of people will say it's not. That's why they're saying weak. It's because there's so many acetal linkages there and not hemiacetals. Okay, amylpectin. Amylpectin is used a lot in canning, making jams and jellies. That's what firms it up. And amylpectin. Sometimes they just say it's pectin, but it's amylpectin. And that is a long chain with branches. So we've got, oops. So at carbon number 6 is where the branch takes place. And glycerol looks exactly like amylpectin with a few more branches, but it's basically a branched chain. Okay, and there's one more polysaccharide, and that's cellulose. And the only difference between amylose and cellulose is the linkage. Linkage here is beta 1,4. These are all alpha 1,4, alpha 1,6. Okay, so those are the biochemicals you need to know. And all the reactions that can go with them, the linkages, etc. So there's a lot of flashcards for this unit. Next unit's gonna have a lot of flashcards too. Okay, so are there any questions about these guys? Now, there are a lot more biochemical structures. These are like the core. There's all different kinds of illegal saccharides. One illegal saccharide has got fructoses instead of glucoses in there. I mentioned that in lecture, but you don't have to know that one. It's just a big variety. And there are 16 monosaccharides. You only need to know 3. And there are as many disaccharides. I need to know 3. So I wanted to have representatives that are the most common ones. Okay, that's what I wanted to focus on today is the biochemicals and their reactions. Monday, I'm going to talk about the non-biochemicals, just the organic ones. Same kind of reactions though. Same kind of reaction. Okay, so that's what I wanted to cover today. And